In the last several lessons, we've been talking about limits quite a bit and in an informal way. We've learned that a limit is the value a function is approaching as the x value gets closer and closer to a certain number. And by now, you've probably developed a pretty good idea of what a limit is. And remember, we can find a limit by looking at a graph, examining a table of values, or we could use the function and manipulate it using algebra. We've also seen how limits connect to continuity. Remember, a function is continuous at a point if the limit exists, the function is defined at a point, and the limit equals the function's value. So in other words, continuity depends on the understanding of limits. We even use this idea when we studied the intermediate value theorem. The theorem only works for functions that are continuous on the interval in question. So that's when the function has no breaks or holes or jumps. It must pass through every y value between the 2 points. And we relied on the intuitive understanding of continuity and limits to apply the theorem. And there's an actual solid mathematical foundation behind those ideas. That's what we're going to cover in this lesson. In this lesson, we're going to take the next step and we're going to look at the precise definition of a limit. Now, this is one of the most challenging ideas or concepts that you're going to run into because you're going to probably encounter proofs for the first time. And we are going to be learning some new symbols as well. So you might feel a little overwhelmed at first, but that's pretty normal. You'll be in good company. We're all going to feel that way together until we start practicing and getting some examples under our belt. So don't worry if that's your first reaction. It's pretty normal. The reason mathematicians created this precise definition is because intuition isn't always enough. Sometimes graphs can be misleading, calculators can round values, and our eyes can trick us. Once we have this precise definition, you'll see that it becomes the foundation of many of the ideas that we've already studied. It gives us the mathematical language we need to define continuity rigorously, justify the intermediate value theorem, and later prove some other important theorems that we're going to encounter in calculus. So that's what we're going to cover today. We're going to start looking at the precise definition of a limit. Before we can understand the formal definition, we need to talk about something else and go back and review something. We need a mathematical way to describe what it means for two numbers to be close together. So if we think about a number line, if I asked you, for example, how far apart are the numbers 3 and 5, you would say they're 2 units apart. If I asked you how far apart -2 and 4 are, then you would say they're 6 units apart. So in mathematics, we measure distance using absolute value. So the distance between any two numbers, let's call them generically A and B. So let's write this down. The distance between A and B, you would write it like this. The other way you can write it is like this also. It means the same thing. You'd get the same answer. All right, so the absolute value makes sure that the distance is always positive because the sign of the number tells us the direction or which side of the number line you're looking at. But when we're talking about the distance between two numbers, we don't care about direction. We just want to know how many units are those two numbers apart. So that's why we deal with absolute values when we talk about distance. So this idea is going to be the foundation of the precise definition of a limit, measuring how close the function is. So we have some symbols to look at now. So if I gave you this expression, so this is the absolute value of f of x minus L is less than E. So we know that f of x is the value of the function. And in this case, I'm using L for the limit. So if I pick some value of x, or I plug it into the function and I get f of x, and I want to see how close that is to the limit, remember we just said the distance between two numbers, we use absolute value. So if I want to find the distance between the value of the function and the limit, I would say f of x minus L and then find the absolute values. Now, if I want it to be within a certain range, and that's the distance that we call epsilon, that's our fancy looking E here, we want it to be within epsilon. So this symbol here is called epsilon. Okay, so this represents the distance between the value of the function and the limit, and we want that to be within epsilon. So if I look at this picture, right here where I'm marking it or highlighting it green, here's my limit. If I want the value of the function to be within epsilon, I want it to fall on the interval between L minus epsilon and L plus epsilon. So I want it to be in this green area that I just highlighted. So epsilon typically in mathematics represents a small positive number, and we usually use that to tell us how close we are to something. So it's just a symbol, just like we use X or we use Y, but a lot of times it has a certain meaning. Epsilon typically means we're looking at a small distance, okay? All right, now let's look at another expression that we're going to need in the definition. We also have this one. Okay, so this tells us the distance between x and a, because it's the absolute value of x minus a. So the absolute value of x minus a tells us the distance between x minus a. We want it to be positive, so it's greater than 0, but we want it to be less than this symbol, which we call delta, which is another way of saying a small number that we're using for comparison, but when we use delta, we're talking about the x values. When we talk about the y values and we're looking at small distances, we use the epsilon, which is that fancy looking E. Okay, so when I look at our picture, I'll use a different color. We want to be within delta of that value of a that we're approaching. So that's why this distance is called delta. So if I look at A and I come out delta in either direction, I want X to be in that interval. That's what this is saying. We also have to make sure, because we're talking about a distance, and with limits, we want to talk about approaching a specific value, not that X is equal to A, that X is approaching A. So we want there to be some distance between the X and the A. It can be really, really small, but we don't want them to be the same exact thing. So we want that distance of delta to be greater than 0. We don't want it to be equal to 0, because that means there's no distance between X and A. So delta always should be greater than 0. We also have some new symbols that you may not have seen before. So when you see this, it looks like an upside down capital A. This is the mathematical symbol for all. And then when you see a backwards capital E, that means there exists. So this might seem a little bit overwhelming because you're getting introduced to a lot of new symbols, but I promise you with practice it's going to start to get better. So let's wrap this up. So before we even start looking at the definition of a limit, we looked at two important ideas. The idea of epsilon, which measures how close the function values are to the limit. So that's the small distance that should be on the y-axis. And delta measures how close the x values are to the point that we're approaching. So that's the small distance on the x-axis. The entire formal definition of a limit is really about connecting these two ideas, okay? So as x approaches some value, we have a distance for delta, whereas x gets closer and closer to a. And then that's going to create a distance for epsilon. Okay, so we're going to make a connection between those two ideas. So if we can keep the x values close enough to a, then the function values will automatically stay close as we approach the limit. So that's the big idea behind the precise definition of a limit. And we're going to start looking at the definition and working it through piece by piece, and then we'll work through an example. So here's the official definition. Let f of x be defined for all x not equal to a. Why don't we care about a? A is the value that we're approaching. We don't care if we actually get there or if the value of a is even in the domain of the function. We are just approaching the value of a. So all we care about are the values that are close to a but not equal to a. Okay? So, and then we're going to assume L is the limit. So if we have the limit x approaches a of f of x is equal to L, we should be able to write out this proof. X says for every epsilon greater than 0, and you might see it written like this, right? Because remember that upside down capital A means for all, and then we have epsilon greater than 0, and then we would say there exists, with the backwards capital E, there exists a delta greater than 0. And sometimes you'll see such that abbreviated as ST, that 0 is less than the absolute value of x minus a, which is less than delta. So if we have all of this, then we would have this, that the distance between the value of the function and the limit is going to be less than that small value of epsilon. So here's the big idea. Epsilon controls the y value, the accuracy of the y value, okay? And delta controls the accuracy of how close you are to the value that you're approaching. The definition of the limit says if you want f of x to be extremely close to L, our limit, we can make x close enough to guarantee that it happens. That's what this is saying. So I have created a template for you to use until you get comfortable with this proof. Now, in Canvas and in the XYZ course, I have posted this template along with some different examples that you can use to follow. Now, whenever we're writing a proof for limit, here's the notation. If I say the limit as x approaches some value of x, we'll call it c of our function, and we're going to call the limit L. So the first part, it's not part of the proof yet, but it's prepping for the proof. 1 and 2 is doing prep work. Step 3 here is when we actually write the proof. So for step 1, we're going to let epsilon be greater than 0. And then we're going to do some scratch work to find our delta, because in order to do our proof, as if you notice in step B, underneath step 3, when we're writing our proof, we need to know what the delta is. So we start with our function minus the limit in absolute values is less than epsilon, and we want to use algebraic techniques to try to get it down to x minus c in absolute value. So this is what x is approaching. X minus c, c is the value that we're approaching. And then whatever we get over here on the other side of the inequality will be what we assigned to delta. All right, so once we find delta in part 2, working backwards, then in step 3, we've done the foundational steps to get this started. And in step 3, we actually write the proof. So to start the proof, you say, let epsilon be greater than 0. Then we state what we chose for our delta. What did we find as our delta in our scratch work? Then in part C, we're going to make the assumption that this is true. And what we're trying to find is we're trying to find f of x minus L and show that that's less than epsilon. So in this proof, our if statement, if x minus, whoops, I got A and C in here. This should be a C so that we're consistent with our notation. So x minus C, whatever we're approaching, if we assume that that's less than delta and we know that delta is a positive number, then we want to show that f of x minus L, absolute value, is less than epsilon. We want to show that the distance between the function value and the limit is super small where it's less than epsilon. So that's our goal. And so we start with this f of x minus L absolute value, and then we use the fact that we know that x minus C is less than delta, that distance, and as long as we can show that we get that f of x minus L absolute value is less than epsilon, which we should because we set it up that way when we did our scratch work, then we can say that we proved the limit. So these are the steps. Again, don't get worried if this sounds like a whole nother language to you. It will come to you with practice. You have to do several examples till you start to get the hang of it, and just ask questions as you're working through these examples. So let's look at our first proof that the limit as x approaches 1 of the linear function 2x plus 1 is equal to 3. So if we follow the template to make things easier, the first step we say we assume that epsilon is greater than 0. And then in step 2, we do our scratch work so that we can find delta. Okay, so we're going to start to find delta. We want to start with f of x minus the limit is less than epsilon. So that gives me f of x, which is 2x plus 1. And I want to subtract the limit, which we know is 3. And we want to say that that's less than epsilon. All right, now our goal is to whittle this down. We want to find x minus an absolute value, whatever value we're approaching. So in this case, since we're approaching x is 1, I'm going to have in here x minus 1. We want to rewrite this using algebra as x minus 1 with the absolute values. So we're just going to use some algebra manipulation, and then whatever we have on the right-hand side of this inequality is then going to be what we let delta be. Okay, so when I clean this up, I'm going to get 2x plus 1 minus 3. If I combine the 1 minus 3, that gives me 2x minus 2. And then in absolute values, and then I have less than epsilon. And then I can factor out a 2, and that's where I get the x minus 1 from. So if I factor out a 2, and because the 2 is positive, I know the 2 is positive, it can just come outside the absolute values. And then when I isolate the absolute value of x minus 1, and I divide both sides by 2, I get on the right-hand side that delta is epsilon over 2. So we're going to choose our delta to be epsilon over 2. Okay, so that's our scratch work. Now in step 3 is where we actually write the proof. So the first step when we write the proof, we want to say let epsilon be greater than 0 be given. And we want to show that f of x minus L is less than epsilon when we assume that x minus 1 is less than delta, which we said is epsilon over 2. So we're going to assume that this is true, and we want to show that f of x minus L absolute value is less than epsilon. All right, so we have f of x, which is 2x plus 1. If I subtract L, we said that that was 3. And now, just like I did before, because we did the scratch work to set this up, I combined the 1 and the minus 3. So I got 2x minus 2. And then I said I can pull out the 2. Now, because I know that x minus 1 is less than delta, which is epsilon over 2, I know that 2 times the absolute value of x minus 1 has to be less than 2 times delta, which is the same thing as saying 2 times epsilon over 2. And when I cross off the 2's, I get epsilon. I started with f of x minus L, the absolute value, and I created this mathematical statement to say that that's less than epsilon, which is what we were trying to prove. So now I can end it by saying, therefore, the limit as x approaches 1 of 2x plus 1 is equal to 3, because we just showed that this f of x minus L absolute value, that distance between the function value and the limit, is less than epsilon.